So in this part, right, we'll be looking at basically what are the main contributions to the CogVLM, as well as we'll try to get into the details of CogVLM architecture. So, so basically, when it comes to CogVLM contribution, right, so it tries to it introduced a visual export module that allows a deep fusion of visual and linguistic features. That is one innovative thought that these guys have used. And the CogVLM size is 17 billion models, 17 B thing, and it uses a language model as a 7 billion parameters. And they have achieved the SOTA cross-model benchmarks across the 17 benchmarks. Okay, so that is one thing. And another one is they have done a good amount of ablation studies in order to in order to validate the effectiveness of the visual export module. That is how relevant visual export module is in arriving at deep fusion. So because they have introduced a visual export module uh, to achieve a diffusion of the visual and the text feature alignment, right, into the deep down layers of the LLM. They also kind of looked into various critical factors in a multimodal pre-tuning as well, like a scale of visual encoder, what kind of attention mask is preferred, like causal mask or full mask, and what are the important parameters in the VLMs, and the need of incorporating a super self-supervised image launch. That is one thing. Okay. So now if you look into the CogVLM architecture, right, there are primarily four important components, right? Vision transformer encoder that transforms image into visual feature space. MLP adapter that projects image features into LLM input space. Another one is the pre-trained large language model and the visual expert module that allows a deep fusion or deep uh, fusion of visual and image features, text features alignment into the deep of the LLM, right? So we'll try to look into the design details of each of those components in the CogVLM. So for example, if we look into VAT encoder, right, it uses a pre-trained EVA to click E in the CogVLM 17. And but it tries to it removed a final layer of the VH encoder because it was specialized in aggregating CLS features for contrastive learning. So that is not needed because we only needed encodings for the image features and the MLP adapter. So the intention or the utilization of MLP adapter is to map the output of VIT, that is image encodings, into same space as the text features from the word embed. That is, it's like aligning text features with the text space. So the architecture of an MLP adapter is two-layer MLP that is adapted in a Swigglue architecture, a Swigglue paper. All image features and for implementational convenience, right? All image features, right? They kind of use the same position encoding in the language model since already the position encoding has been encapsulated in the input of VH. So that is one thing. And when it comes to pre-trained large language model, right? So in the CogVLM architecture, we can use any off-the-shelf GPT style pre-trained large language model. So CogVLM, right? It adapted Vicuna 1.5, that is a 7B model. Okay. And when it comes to attention operations, it adapted all a causal mask. So now we will look into the visual export module. So visual, CogVLM added a visual export module to each layer, each transform block in the LLM, right? In order to enable visual language feature alignment into the deeper layers of LLM. So specifically, the export module has QKV matrix and MLP in each layer, right? So if you look into the matrices shape and all those stuff, right? So what extra it is introduced? Because earlier, without vision module, right, there is LT, the length of the token sequence, and the batch size and number of hits, and the hidden size is same, right? So when we bring image, that is in the CogVLM, what is extra is added is the length of the image tokens. So that's what. Okay, but when it comes to the dimensions of the query matrix, key matrix, and value matrix, because earlier what there is a XTWTQ. WTQ is a query matrix for the text tokens, value matrix for the text, and K matrix with this one. So additionally, we are bringing additional three matrices: query matrix for image, and key matrix for image, and value matrix for image. So now we are going to concatenate for the query features and the query features with respect to image and the text to form a overall query. Similarly for the key and value. So otherwise, the attention, everything else, same as in the large language model. And when it comes to feed forward network, right? So the same concatenation is going to happen. So not much of the difference. So the QKV matrix similar, same architecture as a large language model QKV architecture, similar to the same FFN as well. So when it comes to position embedding, right? So in LLM, it was a rope, a rotary positional embeddings. So in CogVLM, they allow all the visual tokens to have a same position ID. As I mentioned, since the position information already been encapsulated when inputted into the VAT, that is image encoder. Okay, this approach basically kind of mitigates the impact of remote attenuation between the tokens in the LLM. The reason to use the same single position ID for all the visual tokens, right? So the image can occupy thousands of tokens. So using a position ID for every image token results in a lengthy encoding sequence. It would lead a query to focus more on the image sequence closer to it. So that is namely the lower part of the image. So that's why they try to use a single positional ID for all the visual tokens. So that's what they have shown.